Hi, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 52 in the series, Adding and Subtracting Rational Expressions. So if you've picked up on the pattern so far, adding and subtracting rational functions is going to look like the adding and subtracting of fractions of numbers. Recall that if fractions have like bases, you can simply add or subtract the numerators to add or subtract the fractions. That is to say, a over b plus c over b is just a plus c over b. And if you remember the fraction video we did, this is a simple consequence of the distributive property, factoring out a product of 1 over b from a over b, and then factoring that out, adding a and c together, and factoring it back in. So, an easy consequence of the distributive property. However, if the bases are not like, then we can't use the distributive property. And we have to begin by making them like, by unsimplifying the fractions in a certain way. So for example, if I want to add a over b plus c over d, what I could do is multiply a over b by d over d, and c over d by b over b. And the reason this is going to help is because now the bases of both of these fractions are db. Once the bases are the same, you could just add the numerators, but now the numerator has this extra d and b up along with the a and c. So we unsimplify the fraction. Notice this would reduce to a over b. And we unsimplify this fraction, which would reduce to c over d. And then we add the two of them together to get our final sum. And of course, the trick that we're taking advantage of here is that if b and d are not 0, then b over b and d over d are just 1. And we're allowed to multiply by 1 freely. You'd think multiplying by 1 would be a pretty boring trick, but actually, as long as you do it tactically with very interesting versions of 1, you can do a lot with that. Same thing with adding 0 to things. Now, note that you don't have to multiply the entire denominator on the top and bottom. That might not be necessary. All that we really need is to get the bases to match. So for example, if I had a fraction like a over bd minus c over d, then I really don't have to do anything to a at all. All I have to do is manipulate the c over d term. If I multiply that by b over b, then both of the denominators are db, or bd, which is the same thing, commutative property. Then we can take the difference and get a minus c times b over the common denominator of bd. Here's another example of that. If I had a over bd minus c over de, okay, well, they have a matching d in them. Both of the denominators have a d, but this one's missing a b, and this one is missing an e. So I just put them there by multiplying by this very creative version of 1. E over e times this guy here, b over b times this guy here, and then we get all the letters in the denominators that we need. We get d, e, and b, we get d, e, and b, so we can just take the difference now. This is going to be e times a minus c times b over the common BDE. So let's take these examples and patterns forward and apply them to the rational functions, the fractions of polynomials. If I have something like this, x squared over x squared plus 2x plus 1 minus 1 over x squared plus 2x plus 1, well, the bases already match. And so I can just subtract the numerators freely. Now, if I do this, I'm going to wind up with a fraction that I could perhaps factor anew, just like when we do addition or subtraction of fractions. You had to check to see if you could reduce that. Even if the bases matched, you might now have a new term in the numerator that you could check for reducing. Here, the way reducing looks is by factoring the polynomials and canceling common terms. This is the difference of two squares, so I can factor it as x plus 1 times x minus 1, and then that cancels with one of the x plus 1s on the bottom, because this x squared plus 2x plus 1 is really just x plus 1 squared. And once we cancel those, we get this final thing. We should note that unlike when we do division and multiplication, we have to check for this cancellation after we add or subtract. This is because if we're doing multiplication or division, we're going to see cancellation as soon as we rewrite things as multiplication. But when we do addition or subtraction, you have to check for cancellation afterwards too. That means factoring and checking for common terms. So in order to see what kinds of factors are in the denominators so that we know what we might need to multiply by in order to get them like, we should factor those first as well. So here, for example, we have 3x minus 9 over x squared plus 5x plus 4 plus x minus 2 over x plus 4. So in order to see how to make these denominators like, we should factor everything first. And then what we're going to see is x squared plus 5x plus 4 factors is x plus 4 times x plus 1. So there's already an x plus 4 over here. I really don't need to do anything to manipulate that, but there's an extra x plus 1 over here that this second one doesn't have. So that's what we need to multiply on the top and bottom. So now we have the denominators matching, and that means we need to combine the numerators by adding them. This means we're going to have to FOIL out this numerator. You can't just leave it as x minus 2 times x plus 1, because we're going to need to add it to this first numerator, and that means combining like terms. Now, you don't see the like terms when it's in its factored form. You have to expand it to see who's a square, who's an x, and so on. So once we do that, then we can add the like terms together. X squared has no like term. We carry that in. 3x minus x is 2x, and negative 9 plus 1 is negative 8. Can we factor this? We sure can factor that. This factors as x plus 4 times x minus 2. And then that lets us cancel, although this need not happen. In this case, this lets us cancel with one of the factors in the denominator. That gives us x minus 2 over x plus 1. Now, I just want to note, as before, even if things cancel, you still have to omit what would make that canceled term 0 from the domain. So in this case, there's never going to be an x equal minus 4 or an x equal to minus 1 allowed. Even though the x equal to minus 4 doesn't seem to cause as much of a problem here, that means there would actually be a hole in the graph of this original function. Okay, time for the praxis. These are your practical exercises. Pause the video at this time and give them a shot. You're going to want to use the pattern of adding fractions, adding and subtracting fractions by getting like bases, and the factorization of polynomials to help you see what those factors of the bases should be. Remember to try to cancel after you do your addition as well. So pause the video at this time, give it a shot. Okie dokie. Let's see how you did. So in this first problem, we can see that they already have like bases. This is going to let us just combine like terms. We've got plus x squared here to this x squared gives us 2x squared. We have a minus x plus minus 7x, that gives us minus 8x, and a plus 1 plus positive 7, which gives us positive 8. Each of these has a common factor of 2. We should always try factoring out the greatest common factor first. And taking that out, we then have x squared minus 4x plus 4. This factors as the square of x minus 2. And so x minus 2 is going to cancel from the top and bottom, and we're just going to be left with 2 times x minus 2. That you could distribute is just 2x minus 4, and that's where it's going to be done. We should note that now at the end, as at the beginning, x is not allowed to be the value of 2, because that would make this denominator 0. Okay, on to the next one. So this one doesn't precisely have like bases yet. What we're going to have to do is first factor to see what the bases are. This is a difference of squares, so we have x plus 5, x minus 5 here. This one has an x plus 5, but it's missing the x minus 5, so we want to multiply by that on the top and bottom. Once I do that, I have like bases, but in order to add these two polynomials together, I need to FOIL them out. This is going to be x squared, minus 5 minus 3, so that's minus 8x, and then minus 5 times minus 3 is plus 15. Plus, here this will be 2 times 9x, which is 18x, and 2 times 5, which is 10. If I combine those terms, I get x squared plus 10x plus 25, which does factor, that is the square of x plus 5. So one of those x plus 5s cancels, and we have x plus 5 over x minus 5. As before, we should keep in mind that negative 5 is a forbidden value. It is omitted from this domain. All right, let's look at this one here. We need to first factor these denominators so we can see what's going on. And in fact, factoring the numerators as well will help us see some simplification that could be done. Once I do all of that, we can cancel terms from the top and bottom. And we see that really we're just trying to take away x plus 6 over x minus 4 from x minus 4 over x minus 1. So in this case, they have no common terms in the denominators. And what we're going to need to do is take each of the other denominators, bring it to the companion fraction over here, and multiply on the top and bottom. So for example, here I have x minus 1. I needed to also have an x minus 4 in it. So I multiply by x minus 4 on the top and bottom. Here I have x minus 4. It also has to have x minus 1 in it, so we multiply by x minus 1 on the top and bottom. Now, you do not need to FOIL these denominators out. You do not need to FOIL the denominators out, but you absolutely have to FOIL the numerators out. Why is that? Because remember, when you add things or subtract fractions together, they don't have to do with the denominators. The denominator just comes along for the ride once we get them to match. On the other hand, we do have some work to do in the numerator. We have to subtract each and every one of these second terms from these terms in the first fraction. So what we should do is take this minus sign. We're subtracting this entire thing. It's got little parentheses. We should imagine little organizational parentheses around this quotient bar, right? Encapsulating the numerator above this quotient bar. So we distribute this negative sign to each and every term. Don't just distribute it to the first term, right? This is minus x squared, but also minus 5x and minus 6, which is plus 6. Now we can go in and start combining like terms. There's a plus x squared and a minus x squared, so they cancel to 0. Then we have minus 8x and minus 5x. That cancels. That becomes minus 13x. And then plus 16 plus 6, that's plus 22. And what we could see is that there is no x minus 4s up here. There are no x minus 1s up here. You can't actually factor this linear term anymore. So we could either leave it factored on the bottom, or you could expand it. It really doesn't matter at this point. So this would be a good example of a final answer, right, with an expanded base. We should keep in mind that x cannot be equal to 4 or 1, because that would make these denominators 0. But neither could it be any of the things that would have made these previous denominators 0, even though they disappeared. So no minus 4s and no minus 6s either. It's always good to remember at the end here that there are these restrictions on your domain that we inherited from the original phrasing of the problem and that might not appear so obvious now that we've done a bunch of cancellation. Alrighty, that's going to be it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.